The ground fault circuit interrupter, or GFCI, breaker functions by monitoring the current difference between the hot and neutral conductors. It's designed to trip and cut off power when it detects a ground fault, thus preventing an electrical shock. A ground fault occurs when current leaks from a hot conductor to ground, often through a person or a conductive surface. To properly function, a GFCI breaker requires both the load neutral and the equipment neutral, also known as the pigtail, to be connected to the neutral bar in the electrical panel. This dual neutral connection is critical for the GFCI breaker to accurately monitor current flow and detect imbalances indicative of a ground fault. Let's delve into why this configuration is essential. When both the load neutral and the equipment neutral are connected to the neutral bar, the GFCI breaker can monitor the current flowing through both neutral paths. The GFCI breaker measures the current in the hot wire and compares it to the current returning on the neutral wires. Under normal operating conditions, the current in the hot wire should be virtually identical to the combined current in the neutral wires. If a ground fault occurs, some of the current will take an unintended path to ground. This could be through faulty equipment, damaged wiring, or even a person. The current returning through the neutral wires will then be less than the current flowing through the hot wire. This difference in current, even a small amount, is detected by the GFCI breaker. When the GFCI breaker detects a difference that exceeds its set threshold, typically 5 mA, it quickly trips. This tripping action cuts off the power to the circuit, minimizing the risk of electrical shock. If only the equipment neutral is connected to the neutral bar, the GFCI breaker may not be able to accurately detect a ground fault. This is because the current imbalance created by the ground fault may not be sufficient to trip the breaker. In this scenario, the current from the hot wire would return through the equipment neutral to the neutral bar. However, without the load neutral connected to the neutral bar, the GFCI breaker may not see a significant difference between the hot and neutral currents. As a result, the breaker may not trip, leaving the potential for electrical shock unmitigated. Connecting the load neutral to the breaker and the pigtail to the neutral bar bypasses the GFCI protection. The load neutral carries the normal return current from the circuit. When this current is routed through the GFCI breaker, the breaker expects it to match the current in the hot wire. However, if a ground fault occurs and some current flows through the ground wire, this current bypasses the GFCI breaker. The GFCI breaker sees the normal load current returning through the load neutral, but doesn't detect the additional current flowing through the ground wire. This defeats the purpose of the GFCI protection. It's also very important to note that doing this will cause the GFCI to trip, as you noticed, which is a good sign because it indicates the GFCI is doing its job. Understanding the proper installation of a GFCI breaker is crucial for ensuring electrical safety. Incorrect wiring can compromise the GFCI's ability to detect ground faults, increasing the risk of electrical shock. Always follow the manufacturer's instructions and local electrical codes when installing GFCI breakers. If you're unsure about any aspect of the installation, consult a qualified electrician. When installing a GFCI breaker, firstly, turn off the power to the circuit at the main breaker panel. Secondly, identify the hot, neutral, and ground wires for the circuit you're working on. Thirdly, connect the hot wire to the terminal on the GFCI breaker labeled line or hot. Fourthly, connect the load neutral wire to the terminal on the GFCI breaker labeled load neutral. Fifthly, connect the equipment neutral pigtail from the GFCI breaker to the neutral bar in the electrical panel. Sixthly, connect the ground wire to the ground bar in the electrical panel. Seventhly, carefully tuck all wires into the electrical panel and close the panel cover. Eighthly, turn the power back on at the main breaker panel and test the GFCI breaker by pressing the test button. The breaker should trip, indicating that it's functioning properly. Ninthly, reset the breaker and verify that the circuit is working as expected. If the GFCI breaker trips immediately after being reset, there may be a ground fault in the circuit. Disconnect all appliances and devices from the circuit and try resetting the breaker again. If it still trips, there may be a wiring issue that needs to be addressed by a qualified electrician. Now let's discuss the NEC, or National Electrical Code, and how it relates to GFCI protection. The NEC provides specific requirements for GFCI protection in various locations and applications. These requirements are designed to minimize the risk of electrical shock and ensure electrical safety. The NEC requires GFCI protection for receptacles in bathrooms, kitchens, garages, and outdoor locations. It also requires GFCI protection for receptacles serving countertops in kitchens and for receptacles located within a certain distance of sinks or other water sources. In addition to receptacles, the NEC also requires GFCI protection for certain appliances such as dishwashers, washing machines, and electric water heaters. These requirements vary depending on the specific appliance and its location. The NEC also addresses GFCI protection for swimming pools, hot tubs, and spas. These locations are particularly vulnerable to electrical shock due to the presence of water and conductive surfaces. The NEC mandates GFCI protection for all electrical equipment and receptacles located within a certain distance of a swimming pool, hot tub, or spa. The NEC also requires that the electrical system for a swimming pool, hot tub, or spa be installed by a qualified electrician who is familiar with the specific requirements for these locations. It's important to stay up to date with the latest version of the NEC and any local amendments to ensure that your electrical installations comply with the applicable codes and regulations. The NEC is updated every 3 years, so it's essential to have access to the most current version. Now let's consider how GFCI protection works in conjunction with grounding. Grounding is a critical safety measure that provides a low resistance path for fault current to flow back to the source. This helps to quickly trip a circuit breaker or fuse, cutting off power to the circuit and preventing electrical shock. The ground wire is typically a bare copper wire or a green insulated wire that is connected to the metal enclosures of electrical equipment and appliances. It is also connected to the ground bar in the electrical panel, which is then connected to the grounding electrode system. When a ground fault occurs, current flows through the ground wire back to the source. This creates a large current that quickly trips the circuit breaker or fuse, interrupting the flow of electricity. GFCI protection provides an additional layer of safety by detecting even small amounts of current leakage that may not be sufficient to trip a standard circuit breaker or fuse. By detecting these small current imbalances, the GFCI breaker can trip and cut off power before a dangerous shock can occur. The combination of grounding and GFCI protection provides a comprehensive safety system that minimizes the risk of electrical shock. Grounding provides a path for large fault currents to flow, while GFCI protection detects small current leakages. Together, these measures help to ensure electrical safety in homes, businesses, and other locations. Now let's talk about troubleshooting GFCI breakers. If a GFCI breaker trips frequently or unexpectedly, it can be frustrating to diagnose the cause. Here are some steps you can take to troubleshoot a GFCI breaker issue. Firstly, check for obvious sources of ground faults. Inspect the circuit for any damaged wiring, wet locations, or faulty appliances. Disconnect appliances one at a time to see if one of them is causing the problem. Secondly, test the GFCI breaker itself. Use a GFCI tester to verify that the breaker is tripping at the correct current level. If the breaker doesn't trip when tested, it may be faulty and need to be replaced. Thirdly, check the wiring connections. Make sure that all connections are tight and secure. Loose connections can cause intermittent problems and may even create a fire hazard. Fourthly, look for shared neutrals. In some cases, a shared neutral can cause a GFCI breaker to trip. A shared neutral occurs when two or more circuits share the same neutral wire. This can create a current imbalance that trips the GFCI breaker. Fifthly, consider environmental factors. Sometimes environmental factors such as humidity or temperature changes can cause a GFCI breaker to trip. If the problem seems to occur only during certain weather conditions, this may be the cause. Sixthly, consult a qualified electrician. If you are unable to diagnose the problem yourself, it's best to consult a qualified electrician. An electrician has the knowledge and experience to identify and repair complex electrical issues. Remember that working with electricity can be dangerous. If you're not comfortable working with electrical wiring, always hire a qualified electrician to do the job. Now we should mention the different types of GFCI protection. There are two main types of GFCI protection: receptacle type GFCIs and breaker type GFCIs. Receptacle type GFCIs are installed in place of standard electrical receptacles. They provide GFCI protection for the receptacle itself and for any devices plugged into it. Receptacle type GFCIs are commonly used in bathrooms, kitchens, and outdoor locations. Breaker type GFCIs are installed in the electrical panel. They provide GFCI protection for the entire circuit. Breaker type GFCIs are often used for circuits that serve multiple receptacles or appliances. Both receptacle type and breaker type GFCIs provide the same level of protection. The choice between the two depends on the specific application and the desired level of coverage. In some cases, it may be necessary to use both receptacle type and breaker type GFCIs to provide comprehensive protection. For example, a circuit that serves multiple receptacles in a bathroom may have a breaker type GFCI in the electrical panel and receptacle type GFCIs at each receptacle. This provides two layers of protection in case one of the GFCI devices fails. It's important to choose the right type of GFCI protection for the application. Consider the location, the number of devices served, and the desired level of coverage when making your decision. If you're unsure which type of GFCI protection is best for your needs, consult a qualified electrician. And lastly, let's talk about GFCI testing and maintenance. Regular testing and maintenance are essential for ensuring that GFCI devices are functioning properly. GFCI devices should be tested at least once a month to verify that they are tripping as designed. To test a GFCI device, simply press the test button on the device. The device should trip, cutting off power to the circuit. If the device doesn't trip, it may be faulty and need to be replaced. In addition to regular testing, GFCI devices should also be visually inspected for any signs of damage. Look for cracks, discoloration, or other signs of wear and tear. If a GFCI device is damaged, it should be replaced immediately. It's also important to keep GFCI devices clean and free from dust and debris. Dust and debris can interfere with the operation of the device and may even create a fire hazard. To clean a GFCI device, simply wipe it down with a damp cloth. Avoid using harsh chemicals or abrasive cleaners, as these can damage the device. By following these simple testing and maintenance procedures, you can help to ensure that your GFCI devices are providing reliable protection against electrical shock.